We continue with definite integrals. Now, properties of definite integrals. Now that we know a definite integral represents area under the curve, the next step is understanding how integrals behave. Just like addition, multiplication, derivatives follow certain rules. Integrals have rules too. These rules do not make things harder, they actually make integrals easily to work with. So let's go through them one by one in a simple way. Property 1, switching the limits. What do we mean by this? Integral from b to a f of x dx is minus integral from a to b f of x dx. Now we can interchange the limits on any definite integral. All that we have to do is to tack a minus sign onto the integral when we do. So integral from b to a is minus the original integral, which is from a to b. So what does the property say? It says if you flip the limits of the integral, you must add a minus sign. Why? Because switching the direction means you are measuring the area backward. You are measuring it from b to a. So you have to tack a minus sign. So from left to right it is positive, and from right to left it's the same area but negative. Example, the area under the curve or the parabola x squared from 3 to 1 is equal to minus the area of the same function from 1 to 3. Property 2 is telling you about having the same upper and lower limit for the integral. So the integral from a to a of f of x dx will be equal to 0. Means you are not calculating any area. The upper and lower limits are the same. Then there is no work to do. The integral will be 0. And the area is 0, of course. So there is no interval, no width. This means that you will have no area. And now with property 3, factoring constants. If you look at the figures to the right, you can see in figure 1 the graph of the function y equals x squared, a parabola. Also in figure 2, the graph of the function y equals 2x squared, so x squared multiplied by 2. Also a parabola, the shape of the curve does not change by multiplying x squared by a constant 2. And this is our idea. Now let's check what will happen to the area when we multiply the function by a constant. So f of x equals equals x squared. G of x, let's say, is equal to 2x squared. 2x squared, 3x squared, any constant. Now let's find the area between 1 and 4. Okay, of f of x equals to x squared. The primitive of x squared, or the antiderivative, is x cubed over 3 from 1 to 4 here. So it is 4 cubed over 3 minus 1 over 3. So 64 over 3. So it is 63 over 3, 21 units square. Okay, now let's find the area under the curve of the function y equals 2x squared. As in indefinite integrals, as in derivatives, you can factor the constant out. So this is 2 multiplied by the integral of x squared from 1 to 4. You have already found the integral of x squared from 1 to 4. So it is 2 times 21. It is 42 units squared. So the constant can be pulled out of the integral. Constants do not affect the shape of the curve, they only scale the area. So here, since the integral of x squared is multiplied by 2, so the area under the curve of f of x equals 2x squared will be double the area under the curve of the graph y equals to x squared. If it is multiplied by 3, it will be triple. By 4, it will be times 4, and so on. But the shape of the curve does not change. So in general, integral from a to b, c times f of x, sure, c is a constant, will be equal to c multiplied by the integral of f of x dx. C is any real number. So, as with limits, derivatives, and indefinite integrals, you can factor out a constant. So, it's the same idea we use in derivative. Constants do not affect the shape of the curve, they only scale the area under the curve. Integrating a sum or difference, this is property 4. So we can break up definite integrals across a sum or difference. Means integral from a to b, f of x plus g of x. You are adding here two functions inside the integral. If you are adding two functions inside the integral, you can integrate each one separately. So this will be equal to the integral of f of x dx from a to b plus or minus the integral of g of x dx from a to b. And then after that you can add the results. This is obvious. The total shaded area under the two curves combined is the sum of each shaded area. If you look at this graph, this is the shaded area under f of x. This is the shaded area under g of x. Now f plus g of x will be a new function, but the area shaded under f plus g of x will be equal to the sum of the areas under f of x and g of x, or plus g of x. Breaking the interval, property 5. Now this is one of the most useful properties, yet it is too easy. It says that you can break the integral into two pieces at any point c. So if you look at the graph, you have curve, the area under the curve from a to b. You can split it into the area from a to c, then from c to b. So think of it like finding the area from a to b by first finding the area from a to c, then from c to b. So as a result, the integral from a to b f of x dx is the area, or the integral from a to c f of x dx plus from c to b of f of x dx, where c is any real number between a and b.